Okay, so we go to our topic this morning or this day now on lesson 4, which is Newton's laws of motion. Now, the significance of the Newton's laws of motion is that we can now put some factors no or some cause no nga ang nagahulag no why is an object like a car is moving no? Why is it moving forward? Why is it moving backward? No? So the reason why there is motion, no, we will try to give a hint or a factor that causes it. No? So we will use the principles that were laid out by Sir Isaac Newton. No? I think Isaac Newton is an English guy, and in his time he was attributed also as one of those people who contributed a lot in the development of calculus. No? So there's a similar guy like him in Germany. No? I think his name was Leibniz. However, Leibniz formulated also a lot of things on calculus. No? But between him, Newton and Leibniz, Newton became famous, and maybe was attributed a title called, I think, Father of Calculus. Because primarily, he's an Englishman. I think England right at that particular time is one of the strongest country in the world, probably, or they have the hold of a status in the science field. So Newton made also other than calculus a huge contribution in the field of physics. So let's listen to these different laws that Newton contributed. Now, let's consider a body here which is at rest. And a body at rest does not mean that there's no force acting on it. Actually, a body that is at rest may probably be acted on by several forces, not only one, but two or more. Just like when we are seated right now in front of our laptop or computer, you are sitting there, and maybe you can describe yourself to be at rest, but our state of being at rest does not mean that there's no force that is present on us. Now, if you can imagine the amount of air above us, that amount of air above us is enough for us to be pressed on the ground. And that is a force that is exerting on us. That's what they call, I think, atmospheric pressure. There's that weight of air that is pressing us down. So that alone is a force that is acting on us. But the question is, are we moving? So maybe that force is not enough for us to move. So that's why we remain at rest. So perhaps forces alone may not be enough to make motion unless they are sufficiently large to cause the body to change its state. So here is a body that is having a state of being at rest. So what we see here is that the forces that goes to the right, and assuming there's a counter force going left, and if they happen to be the same in magnitude, then we realize that the resultant of these two forces horizontally acting on the body will simply cancel out each other, and therefore ending up with a resultant force of 0. So supposing F1 is equals to F2, and they are acting in the same plane, but in opposite direction. So if F1 going right is subtracted by F2 going left, and they have the same magnitude, the resultant then will become 0. So that's, again, if you remember your resultant force. So here, the resultant is 0, and therefore the body remains at rest. Now, in an initial state of a next body here that is at rest, but for some reason, a bigger force, F2 is acting 50 newtons to the right, and then a counter force of F1 goes left 30, then we will see here that motion will now cause this body to change its state. So from being at rest, the body will now move because there is now a resultant force of 20 newtons going to the right. So that external force will probably cause the body, to accelerate. So again, this one happens because the forces that are involved are no longer equal in magnitude. So again, a body will change its state from being at rest to being in motion once forces are what we call unbalanced forces. Now, the one that we see above may be described as a balanced forces. F1 and F2 equal, but they are opposite in direction. So no resultant. R is 0. So here now we see that forces are what we call balanced forces. Number 2 example is an example of an unbalanced force. And now our balanced forces will have a total effect, or the resolution of their forces, or their resultant force will be equal to 0. However, when they are not equal to 0, like 20 newtons is still present, and it is moving to the right, it simply shows that the body will have a tendency now to move. So the two examples of balanced and unbalanced forces in this case, it may be in motion. So in this next slide, a body may be in motion, but we can also say that there are forces acting on the body while it is moving. Now, supposing there are only two forces acting on the body here, and this body is already sliding, either sliding to the right or sliding to the left. But two forces are present, and these two forces happens to be equal to each other. Now, we can say that if they're equal to each other, their resultant will also be 0. So if F2 going right minus F1 going left, and they are equal in magnitude, then there's no resultant remaining there. That is if we try to calculate the resultant. Now, in this case, if the resultant is 0 and the body is in motion, the body there will move with uniform motion. So that's one of the types of motion that we mentioned earlier. So we can achieve uniform motion when the forces acting on the body will have a resultant of 0. So the body there will have a steady and the same or constant velocity. So its speed and its direction will be maintained, or it will always be the same. Now, in the event when the body in motion will have maybe two or more forces, and these forces are no longer equal in magnitude, then we will realize that the resultant there will not be 0 anymore. So the resultant here, if we will subtract 50 with 30, since they are opposite in direction, we will have a body that will be accelerating. So this one is already having a velocity, or an initial velocity. Now, when an additional 20 newtons is present, the body will therefore accelerate, or its speed will now increase. So from an initial velocity, it will now go up to a higher value. Okay, so if that force, however, is in the other direction, so if the body is sliding to the right, but its net force is going left, then we will notice that the body there will now slow down. So the presence of this resultant force will either increase the speed of the body, or it will decrease the speed of the body. Either the body will speed up, or it will eventually slow down. So we call FR here as the external force. Others call it as the net force or the net external force. So the net external force is creating or causing the body to either speed up or to. Okay, so here is the word F net, or the net force. Sometimes we call it as the unbalanced force, which we referred to in our previous slide. And this means that two forces. So if we will try to simplify our discussion and we will only focus on two forces to easily understand the net force, then the two forces, once they are not equal anymore, will have a net force in a particular direction. So here is the law of inertia. No? So we call the law of inertia now, or describe the law of inertia, which is also known as the first law of Newton. No? Now, it is described, or it is expressing or telling us, no, that a body that is at rest will remain at rest, no? Or a body which is already in motion will continue to move with constant speed or velocity, no, in that same direction, no, unless a force or a net external force will be present, no? Or there's an acting external force. No? Now, what is the effect of this net external force? It will change the direction of the body, no? Or it will cause the body to stop, or it will cause the body to increase its speed. No? Now, we feel or we observe this force of inertia now when we are in a particular vehicle. No? In a car, for example, no? When you are seated in a car and the car is running fast, no? And all of a sudden, no, the car will stop. No? When the driver no, steps on the brake no, for some no, sudden way, no, then you will immediately feel no, that there's this tendency of the people inside the vehicle to be thrown forward. No? So that's your tendency, no? Because you are all in motion, and suddenly no, the thing that you are riding on stops, no, or tries to stop. So all of you will try to continue moving forward, no, despite the fact that you are all buckled, no, or may seat belt ka mo gina-wear sa inyo bangko, no. Because of that harness, no, that keeps you no from moving forward, then you will just tend to cause your body to no ang imo lawas lang ang mahilay forward. No? Okay, but I think no your seat belt will try to prevent no your additional motion. No? So inertia is that property of the body, no, to either remain at rest or to continue moving, no, with constant velocity, no, when there's a sudden change in the vehicle. No? Now the mass of our body, no, is a measure of its inertia. No? The greater the mass, the greater is the inertia, no, or the resistance to change the motion. No? And this is how we will probably understand no, the effect of mass. No? Now, if there are two people in the car seat, no, so in the passenger seat of a car, no, one an elder lady and one is a small kid, no, in the back seat, no, they are seated behind the driver, no, or the front passenger. No? Now you'll notice that since they have two different masses, no, when the car suddenly stops moving, no, you'll notice that the little kid will have a bigger chance of no being thrown forward. No? Maybe no the more massive passengers, no, like an elderly individual, no, dako siya, dako iya mas, gamay lang ang iya nga change ang iya nga movement, no, when the car suddenly stops. No? But usually, no, babies and those smaller kids, no, will have a bigger tendency to be thrown forward. No? So again, in a vehicle, it is always no advisable, or it is always no you are being reminded that if there's no seat belt for small kids, these small kids should be held no closer to bigger people. Uyatan mo ginasa, no? Kaya again, ang tendency sina no is to be thrown no much faster no kung gulpi magdalagan ng salakyan no? Or magpundo. No? Okay, so mass is a measure of the inertia no, of a body. No? Okay, now let's look at the mass of the body now and the force present, and looking at the effect now on what we call acceleration. Now, if we consider these two instances where we have two different forces, no? So M1 is being acted on by F1, no? A force F1, and F1 is much more smaller no? Than F2. No? Looking at the length of the arrow, our F2 is much more greater in value than F1. No? Then we will see that if M1 and M2 are of the same mass, no? M1 and M2 are equal in mass, no? Or number of kilograms, and F2 is a bigger force compared to F1, then the acceleration will not be the same. No? Now, the body with a greater force will tend to have a greater acceleration. No? So in this case, acceleration 2 or A2 will be bigger than A1. So what's the factor that affects the greater acceleration? It is the force, no? So maybe we can say that acceleration and force, no, are directly proportional to one another. No? So if you want to increase the acceleration, then maybe you can increase also the force that you apply, no, on a given body, no, or what we call the net external force. No? Now, if we will try to consider, no, another factor, and this time mass, no? Mass number 2 is greater than mass number 1. No? And if we will apply the same amount of force, no? If F1 and F2 are of equal magnitude, no? But masses M2 and M1 are not the same, no? M2 being larger, no, than M1, that acceleration will now, no, become different also. No? So parehas ang amounts ng force, pero ang mass na gina-applyan natin are two different values. No? So what is the effect on the acceleration? So acceleration will now be slower, no, or lesser in A2 than in A1. No? So again, no, acceleration and mass, they are inversely proportional. No? So kung ang body mo dako-dako nga bus compared to a car, no, or a motorcycle, no, when they are in that traffic light, no, and all of a sudden the color of the light changes from red to green, no, then I think now the smaller body or the less massive body, you know, like a car or motorcycle can, no, accelerate faster than the bus. No? Okay, so the effect of mass to our acceleration. No? Now, if we combine together, no, the relationship of acceleration to force and mass, no, then maybe, no, this net external force can be equated to the product of the mass times its acceleration. No? So the value m times a is now equals to F net, no, or the net external force F, no, the one that is in the red box. No? This equation, this sum up equation F equals m times a, no? you are probably familiar to that, no? And we call that as Newton's second law. No? And among the laws of Newton, no, the law of acceleration or Newton's second law, no, is the one which will have an equation. No? The two other laws, no, number 1 and maybe, no, the third one later, we will not have an equation for it. No? So here's the statement of the law of acceleration. No? So if a net force or an unbalanced force acts on a body, no? So if the forces, no, F1 and F2 are no longer the same, no? And they will have a resultant, no? What's the effect? The body will accelerate. No? So acceleration can either be speeding up or slowing down. No? Now the magnitude of the acceleration is directly proportional to the force, no, but it is inversely proportional to the mass of the body. No? The direction of the acceleration is also the same, no, as that of the net force. No? Now, another way of saying the law of acceleration, another way of saying it is that mass and acceleration are inversely proportional. No? So that's another way of saying it. No? So this is the second law, and again, the second law is about, no, an equation, no, which we call as F equals m times a. No? Now the third law, no, is the law of interaction. Others, I think there are some texts that calls it the law of interaction, but I would rather prefer to call it as the law of action and reaction. No? Now, just like when we are sitting on a table, no, or sitting on a chair, for example, right now, no, on a stool, your weight is being pulled by the earth, no, but the chair that you're sitting on is pushing you upward, no. So that's an action and a reaction principle. No? So what is the action there? Maybe your body weight, no, going down, and the reaction or the supporting, no, force, so that hindi ka mahulog sa salog, no. So the chair will now push you up. No? Now, if the chair is not strong enough, then maybe it will give way. No? Mabali na dayatiil, no? And then therefore, you will fall on the ground. No? So, but unless otherwise, no, it can hold you up. No? Then you will remain seated, no, in your chair. No? So That's one typical action and reaction principle. No? So when an object exerts a force on another object, no, the second object will always no, exert on the first force no, the same force but opposite in direction ng iyang magnitude. No? So the same magnitude of force, but no, it will be going in another direction. No? Like pushing a wall. No? There's nothing that we can actually do no, if we push a wall that is large enough. No? But you'll notice that the force that you exert on the wall will cause the wall to push you back. No? So an action and reaction principle no, may be present there. No? But we are not actually seeing no, the wall moving no? Because the wall is strong enough. No? But definitely if you push the wall will push back. No? So there would be an equal amount of force that will be pushing in the other direction no? To counter your push no? On the wall. No? So again, action and reaction. So for every action, there's always an equal but opposite no? Reaction. Okay, so tod kita, no? You were disconnected. No? Sorry, again. So again, now we go to the law of action and reaction. No? So just like when we said no, about the wall, no? Pushing the wall. No? So the wall will always no, exert a force that is opposite in direction, no? Equal to the amount of force that we use no, to push it. No? But you'll notice that no matter how you perspire, no, pushing the wall, no, the wall will never budge. No? It will never move. No? Because again, no, it's constructed and it's so strong enough, no, hindi na siya mag-idog. No? Okay, now for our first sample problem. So a force of 15 newtons no, on a body no, whose mass is 90 kilograms, find the acceleration. We will find the acceleration of the body. No? So if our equation F net no, is equals to ma, or mass times acceleration. So acceleration can be determined by dividing no, F over A. No? So again, no, if you divide that, no, so if Newton is a force, no, that's our unit of force. So that's equals to kilogram meter second square. And if mass is in kilogram, then you'll notice that kilogram and kilogram cancels out. No? And therefore, no, what remains is we will have a unit no, in meter per second square. No? A unit of our acceleration. No? So makancel ng kilogram. No? And therefore, no, we will end up with 0.17 no? Meters per second square. No? Now, if our unit is in dynes, no, a unit of in dynes is in gram, centimeter, and second square. No? But however, now for now, we have not used it as a unit of our force. No? But units of forces could also be in Newton N or in dynes. No? This word, no, complete word in dynes. No? Now let's have number 2. No? A body starting from rest acquires a velocity of 18 centimeter per second. No? So this time, we will see that our unit here is in the CGS unit. No? And centimeter will always go with grams and will go with a unit of time in seconds. No? Now, if a body has a mass of 15 grams, we will determine the net force F no? Exerted on the body. No? Now, I think the first thing that we will have to find is the acceleration. No? So if acceleration no, is equals to, if we will solve for acceleration, no, then acceleration could be determined by dividing final velocity with time. No? So where did VF equals AT come from? It's equals to VF equals VI plus AT. No? And since the initial velocity can be understood to be zero because it starts from rest, then we can solve for A. No? So A is VF minus VI all over T. No? So dividing therefore 18 centimeter per second with 3 seconds. So the acceleration of the body is 6 centimeter per second square. No? Now using that acceleration to find the force, then we will find the force by multiplying 6 centimeter per second square with 15 grams. No? Now notice the unit dynes. No? So 90, you may think of 90 as a very big number. No? But actually, that's simply equivalent to some 15 grams of mass. No? So actually, dynes, we don't usually use the unit of dynes as a force because we may end up with a large magnitude of value that looks large, but in reality, it's not really that big. So, but anyway, that's another unit of our force. So again, in solving number 2, we use our rectilinear motion equations and use it together with the second law of Newton, which is the law of acceleration, F equals ma, to solve finally for F. Now going to number 3. Let's see our number 3. So number 3, if a net force of 60 newtons is applied horizontally on a 40 kilogram object, what is the velocity of the object after 6 seconds? And another question, what distance does it travel after 6 seconds? So if you're given 60 newtons as a net force, we will also understand here that the 40 kilogram object is not acted on by only a single force of 60. So this 60 newtons is already a resultant. So maybe 2 or more forces na present is acting on the 40 kilogram, but not necessarily a single force. But if we look at it, that single force or that net resultant force of 60 is present on a 40 kilogram object, then therefore, by dividing F net by M, F over M will give us acceleration. So 60 divided by 40, that gives you 1.5 meters per second square. Now, if our first question is asking us for a final velocity after 6 seconds, then we can plug that value 1.5 meters per second square to our equation AT. So 1.5 times 6 now gives you, after 6 seconds, a velocity of 9 meters per second. So this is how fast the body is now moving after 6 seconds. Now, how far will it travel for 6 seconds? So we will solve for S. So S is VIT plus 1/2 AT square. Since V sub I again is 0, then we can simply use AT square divided by 2. And substituting our value, this will now be our acceleration times a time of 6 seconds square divided by 2. So that's equal to a total distance of 27 meters eventually. So again, this is where we see the connections of other lessons in physics, our lesson in motion and our present lesson on Newton's laws. So somehow in our future lessons of physics, we will see them to be kind of intertwined also in our application. Now let's look at this body and this body now involves an M1 body that is on a table that is held on by a cable or a string. That string is passing through a pulley. So this round black object is a pulley. This pulley, which is holding the string, is pulling this M1 object, which is 7 kilograms, to the right, because we have suspended another object M2 on the other end of the string. So this M2 now, which is 4 kilograms, will definitely simply go downward. Now maybe if the table here has some force called friction, then maybe it can hold this mass number 2 below, no, in its place, no. But if the table that we have above, no, is frictionless, there's no friction between the box and the table, then this body will simply slide to the right, no, because nothing will keep it from sliding, no? Now, to make things simpler, we will eliminate the idea of friction, no? Now, we understand that in a real life situation, friction is always present, no? So what we will be assuming here, no, so we will avoid, no, complicated terms like friction, no? We will probably, no, assume, the word is assume, no, that there is no friction present between the box and the table, no? Now there is no friction in air, no, between this M2 and again, no, its environment, because it is suspended completely in air. So this M2 object will naturally simply go down, no? Now, if you'll try to look at, no, our object M1, no, and try to separate it, no, then we can have there, no, a body which we can actually call, no, a free body diagram, no? And allow me to explain what's a free body diagram, no? Okay, so we've made here, no, again, no, so to simplify our complicated diagram earlier, no, we will try to separate, no, our mass 1, no, and we will draw what we call FBD1, or free body diagram 1, no? So FBD is short for the word free body, no, diagram, no? And we will try to look at now the presence of forces, no, on this free body diagram 1, no? Now, free body diagram number 1, which is the 7 kilogram mass, is being pulled by a string to the right, no? Because there's again a pulley on its right, no, and there is a mass below it, no. But if we will separate now the effect of that string will simply create a tension, no? Tension is a force, no, that pulls the body away, no, or it's a force that is pulling away from the body, no? So this is our symbol for tension, no? We indicate it with letter T, no? So again, now when you drag things, no, you are exerting tension there, no? Now, another force present will be W, which is equal to our weight, no? And usually, to determine weight, no, so weight W, no, is determined by multiplying, no, the mass of the body, no, times the acceleration due to gravity, no? So these are the two values that we simply multiply, no? So if we'll try to determine our weight 1, no, weight 1, no? For weight 1 will be 7 kilograms, no? And then we multiply it with 9.8, no? That's meter per second square, no? How much will be the value of our weight 1, no? How much will be the value of weight 1, no? If you'll try to find out, no, the value of weight 1, no? So the value of our weight 1, no, which is going down, no? Weight is always directed to the center of the earth, no? The tension is going to the right, no? So the weight is 68.6 newtons, and then we have a value of tension, no? Now our value of tension is probably not the one that is causing the motion, no? The weight is not creating any motion, no? Because this one, no, this object is held on a table. So weight 1 is not causing any motion at all, no? So therefore, we can simply say, no, that the one responsible for moving the body is T1, no? T1, since that's equals to the net force, no, we know that T sub 1, no, will be equivalent to some value M times A, no? So if it's equals to F net, no, then we understand that it must be some value M mass, no, times A, no? And the mass there should be M1, no? Now, the body here is connected, no? Nakasugpo na sila, no? So therefore, if we'll try to find our T sub 1, no? Atong T sub 1, no? Since it is connected to the mass na 7 kilograms, it must be equals to 7A ang iyang expression, no? A again, no? For your acceleration, no? That acceleration value, by the way, is not yet determined. We don't know that yet, no? Okay, so again, no, T sub 1 here that is in the box, no, is a result of net force, no, M1 times A. No? Now, what about if we will go for another free body diagram number 2? No? What will happen to our free body diagram number 2? No? So let's check now our number 2 equation. No? So for our equation number 2, no, most likely now we will have another free body diagram. No? Now, what's the shape of our free body diagram for number 2? No? Our number 2, no, for free body diagram number 2, we have there M2, and our M2 value, no, is equals to 4 kilograms. No? This 4 kilograms is directed vertically. No? One force is the string, no, that still no pulls it upward. No? So this, we can call this probably as T sub 2. No? So this is our tension 2, which is due to the string that pulls it up. No? And then by virtue of its own weight, no, this mass is also being pulled down. No? So we can call the weight here as W2. No? Now, determining W2, weight 2, no? So here, now both forces are vertical. No? So therefore, since this is vertical forces, no? For our free body diagram number 2, our net force is not the same as free body diagram 1. No? So for free body diagram number 2, our net force here, now we can see our net force to be equivalent to, no, our value weight 2, which is probably no bigger. Okay, this one will go down. No? It will counter the effect of T2, no? Above. No? Now, since we believe the body will go downward, no, then maybe weight 2 must be larger than T sub 2. No? But there must be T sub 2, no? Tension. No? Now, what's the value of this net force F net? F net, no, for free body diagram number 2 will be equal to our M2, no, mass number 2, multiplied by A. No? And how much is our mass 2? So for our next equation, we have F net to be equals to mass number 2, 4 kilograms, no, times A. So 4A siya, no? However, F net is weight 2 minus T1. No? So that's, T sub 2 equals to 4A. No? So again, this is weight 2, and then this is tension 2. No? So if we'll try to determine our weight 2 here, no? So weight 2 is 4 times 9.8, no? Which is a constant value. That's 32.2. Was that what you said?
39.2, sir.
Sorry, 39.2. No? And this is in Newton. No? Now, guys, we were able to come up with an equation earlier. No? First equation was this. No? T1 is equals to 7A. And we have another equation that we come up with to be equals to W2 minus T2 equals 4A. No? However, we already know the value of weight 2. Weight 2 is 39.2, no? minus t sub 2. And this is equals to 4a. No? Now, if we'll try to get the value of t2 actually now by transforming, maybe we can end up with a value like this. No? So let me just use my algebra no, by transferring some equations here. No? So we will have here now no, a value which is 39.2 no, minus 4a. No? Ang natin nga value para no? That will be our value now. No? Okay, so we have two values here that we come up with now. And therefore, now if we end up with another equation here, now, what can we say about the relationships of tension 1 and tension 2? No? Now, we see that tensions 1 and 2 are due no, to the string no, that is attached to our object 1 and attached to our object number 2. No? And since it is a system, sugpon na sila, no? Then we can actually connect the two. No? We can actually link them. No? So in reality, now we can simply say now that maybe now our T1 is just equals to T sub 2. No? And if that's the case, no, then 7a can be simply equated to 39.2 minus 4a. No? And therefore, we could have here 7a plus 4a no? Is equals to 39.2. So we can solve a here no? To be, I think, no? 11a to be equal to 39.2. So dividing both sides by 11, then we can solve for the quantity or the variable a. No? Now, if we try to calculate a, 39.2 divided by 11, no? A is equivalent to how much?
3.56, sir.
This is an example of a problem called a system. No? They are connected by some wire no, or cable. Therefore, they will move together and they will move with the same acceleration. No? Now, the same tension is also present, but in this problem, we simply call it initially no, as T1 and T2, no? So that we'll be able to separate our object 1 from our object 2. No? So okay, now in this problem, now we apply the idea of the free body diagram. No? So we make a separate drawing for object 1 no? And a separate drawing for object 2 and show no, the forces that are present in each body. No? Now with these forces, we show the net force no, that is acting on each body. No? And using Newton's second law, mass times acceleration no, to describe our net force. No? So that's how we approach solving the problem. No? So running through again with our solution, no? So our net force is equals to tension 1 no? For the first body, while in our free body diagram 2, there's two forces present, no? Weight and tension 2. No? The difference of weight 2 minus tension 2 no, is the net force for body number 2. No? But I believe no, the two net force value are simply equal to one another. Okay, then therefore, when we solve for the net force, no, since that's equals to T1, that's equals to mass 1 times A for our first object, no? But our second object, M2, our net force, which is W2 minus T2, is equals to M2A. No? And substituting our value, this is what we got. No? This is what we got. No? Okay, so therefore our answer here is equals to 3.56 now meters per second square. No? So again, I provided you with some diagrams there, no? How we come up with these different equations. No? So if we'll try to solve for the tensions now, no? The tensions must be the same. No? T1 and T2 must be equal, and that's equal to, no, 24.92 if we multiply 7 kilograms times 3.56. No? Okay, so this is our tensions present. No? So actually, we can simply call the tension there simply as T. No? We don't have to put subscripts there, no? Because again, they are connected anyway by a wire. No? Now, I will give you now this next problem to think about. No? So this one now is having two masses also. No? So again, now in our solution here, we will employ the free body diagram idea. No? We have two drawings, no? Two boxes. So on our left is our 4 kilogram mass. On our right is our 6 kilogram mass. There's a tension due to the string now that is going up. No? See the diagram here in the middle. There's T1 and T2. Now we know that they are equal because no, they are connected no, in one connected string. No? So therefore, we can just simply eliminate the subscripts T1 and T2 and just call it T. No? Now, the weights of the body here, weight 1 and weight 2, we will try to find them out. No? And can you please no, determine its value for me? So we get our weights 1 and weight 2 no, by multiplying mass 1 with gravity or acceleration due to gravity. No? So that's 4 times 9.8 and on the other side 6 times 9.8 giving us 39.2 newtons and 58.8 newtons no, for both sides. No? Now, we know that from our Newton's second law, we have F net no, to be equals to MA. No, that's our general equation. But for our free body diagram number 1, that F net is due to T that goes up no, minus weight 1 that goes down. And we believe that this one is a lesser mass. So the tendency for its acceleration is to move upward. No? A on the left side is going up. No? So if you will multiply M, no? M being 4 kilograms times A, our A is going up. So we will have an equation like this. No? Now, substituting, that will be T minus 39.2 no? Equals to 4A. No? And again, 4A because A is going up. No? So we will serve that as equation 1 natin. On the other side here, for our free body diagram number 2, we could have this, a similar equation F net no? To be equals to MA. No? But our F net here is T that goes up minus W2 that goes down. No? And this is equals to M, which is 6 kilograms times A. No? But however, A here is going downward. So therefore, we will put a sign there, negative. No? Do you follow me? Now, why negative? Because acceleration on free body diagram 2 or object 2 is downward. Now, substituting, that will be T minus 58.8 no? Equals to negative 6A. No? And this will now be our no? Equation 2. No? Now, if we express both of them in terms of T, then that will be equals to T equals to negative 6A plus 58.8. No? And our other equation on the left side, we can also equate T here no? To be equals to 4A plus 39.2. No? And therefore, if T is equal on both sides, then we can simply equate that. No? And therefore, we have 4A plus 39.2 would be equated to negative 6A plus 58.8. No? And combining all A's together on the left side, so you'll have 4A plus 6a no, is equals to 58.8, then minus 39.2. Okay, so again, now combining all the a's together gives us 10a, whereas combining 58.8 with 39.2 no, gives us 19.6. Therefore, if you divide both sides by 10, then we'll see a to be equal to 19.6 divided by 10. That will be 1.96
1.96, sir.
meter per second square. No? So that's how fast is your acceleration. No? So the body is not really moving very fast. No? Now, if you'll try to find the tension, then we can use either the equation here on the right side or on the left. No? So let's say we'll solve for T. So T is equals to 4 times 1.96 no? Plus 39.2. No? Okay, can somebody solve that one, please? So the two values, therefore, that we are solving, no? So if we substitute 1.96 to the value of A no, on the left side equation, so 4 times 1.96 plus 39 no, gives us a tension now equal to 47.04. No? And this is our value of our acceleration no, for this problem. So the acceleration on the right side is going down, however, but the acceleration on the left is going up. No? So the only difference is their direction. No? Okay, so this is our problem number. Let's see our solution. So for our solution for number 5, without the free body diagram, no, then we see that, of course, no, we have the weights to consider. And here is our equation. No? For our weight 1, no? Then we still get this value. No? And we'll see that A, no? We can solve our A value and get no, an answer, which is roughly 1.96. No? So our tensions, again, are the same. And our acceleration will be 1.96 no, meters per second. And our tension is 47.04 no, newtons. No? Okay, so this is our other solution. No? But I think no, it's much better or clearer when we have the free body diagram no, illustration. No? Okay, I think you can try this one. No? So for our last number, again, our solution. No? So for the elevator problem, so how much is the tension on the cable when it is at rest? Then the tension must be equal to the weight. Huh? So kay why siya nagahulag? There's no acceleration. Huh? So the tension and the weight are simply equal to one another. Huh? Now, if it is, again, now going upward, no, then it must be slightly higher than the total weight inside. No? Now, if the weight is 3,000 newtons, no, then you will be adding no, that value of the acceleration and the mass of the body. No? So how much is the mass? Mass, again, is weight divided by 9.8. No? So that's why we divided 3,000 by 9.8. Then multiplying the mass, which is 306 no, by 2, gives us 612. No? So that's the one that we add. No? So therefore, the tension must be bigger than the weight. No? So it must be more than 3,000. No? So that's 3,612. No? 0.24. Then therefore, the body will now go up. No? Or the elevator. No? Now for the elevator to go down, no? We have also this number. No? So the tension there must be less than 3,000. No? So the previous value that we added is now the same value that we now subtract. No? Okay, so I think now that's the discussion on our Newton's laws of motion. Now next week, now we will go into momentum. No? So please do not miss our class next week no? For the last lesson on momentum, impulse, and momentum.